Hello, my name is Keegan Faraday, and this is my lab for Faraday's Law for Physics 2212. Now for the introduction, the purpose of this lab is to collect data on a magnet falling through a conductive tube, computationally model the interaction between the magnet and the tube, and compare the observed data to the computational predictions. And as you can see, there is an overview of the results on the bottom. There were three main fundamental principles and a few minor ones that I won't go into. Firstly, Faraday's Law, which relates the time-varying magnetic field to a Curly electric field, which is seen in this experiment. Lenz's law, which states that the direction of the magnetic field produced from an induced current is opposite to the direction of the external magnetic field. And magnetic flux, which measures the total magnetic field in a given area. As for the procedure, first, mark the north pole of the magnet using a magnetometer. I apologize if I butchered that. Secondly, measure the length, radius, and width of the aluminum foil. Third, orient the aluminum foil and position at the opening at the top of the cylinder. Fourth, record 5 sets of data for the time it takes for the magnet to fall through the aluminum foil. And fifth and finally, record both the data and its average on paper and notes to use later and compare to the computational model. As for the system and surroundings, the system was the magnet and the aluminum foil, and the surrounding was everything else. As for the data and measured values, for the aluminum foil, the length was 0.305 meters. The width was 0.006 meters, the inner radius was 0.017 meters, and the radius was 0.023 meters. The magnetic moment of the bar magnet was 2.11, and the mass of the magnet was 0.0185 kilograms. Now for a quick lab question, why not use a ferrous tube? And the reason being, a ferrous tube contains a metal, typically iron, that is ferromagnetic, which means there is already an internal magnetic field, which creates a different interaction with the magnet falling through the tube. And here we have just all of the glow script code that went into this lab. And following the code, we have the results, which was the diagram on the left, which shows you the north and south poles of the magnet as it falls through the aluminum foil. And you see the velocity versus time graph, where you can see there is a long stint of constant velocity, which tells us that the net forces of the magnetic force and gravitational force canceled out to have constant velocity. Now, as for the calculated and observed data, we have with trials 1 through 5 and the average all being between 1.32 and 1.39 seconds. And the data from the glow script gave us a value of 1.375 seconds, which was very similar. As you can see on the left, there is a long-winded question which really is just asking which color corresponds to clockwise current and counterclockwise, and how can you know? Well, the red or the bottom corresponds to counterclockwise, and the blue or the top corresponds to clockwise. And the reason we know this is Lenz's law. For example, with the blue, the magnetic field is pointing upwards, which is opposite to the charge of the magnetic field produced by the bar magnet. This means that its current has to be clockwise. As for what happens to the dynamics of the system when you flip the magnet around, when the magnet is flipped around, the dynamics of the system don't change. Now for further interpretations, the shape of the curve tells us that once the bar magnet is in the tube, there's an additional force acting on the magnet that is opposite to the gravitational force. The forces in the tube must be the magnetic force and the gravitational force. Since velocity is constant, when the magnet is fully in the tube, the net force from the magnetic and gravitational force must be 0, as we saw in the graph. Now for this other question, the total time in the tube of the real-world system was fairly close to that of the computational. The computational was 1.375 seconds, and the real-world average was 1.36 seconds. The computational system can be made more accurate by considering the measurements of the bar magnet. Now for the additional questions. For the first one, we can use Ohm's law to see that current is equal to potential, or EMF, over R, resistivity. So with a resistivity close to 0, the current would increase to a very high number, and the magnet would fall very slowly. In this situation, ideally, it would even stop. And as for the second question, with holes or slots in the tube, there would be less of an induced magnetic force. There would be less ring currents, and the magnet would have a shorter average time to fall through the tube.